Hello and welcome back to another lecture video, this time what corresponds to a calculus-based Physics 2 class, Chapter 9, Electric Current and Direct Current Circuits. DC is short for direct current. So we've got several slides to go for this chapter and the next chapter, all very interrelated, so let's get started. Let's first talk about what exactly is electric current. Let's define it. Okay? So electric current is going to be the motion of charges that gives rise to electric current. It is given by the symbol capital I, and think of it as the rate at which charge flows. Okay? So imagine you have a cross-section of area where charges are moving through this cross-sectional area. And again, I've said this in earlier videos, typically conventional current, that is I with an arrow, is defined as the same direction of motion of positive charges. Again, we know that if positive charges move to the right, that's mathematically equivalent to negative charges moving to the left. And again, we retain the so-called conventional current or the Ben Franklin convention, where let's imagine that positive charges are the ones that are actually moving. So the equation for average electric current is going to be the change in charge over the change in time. And delta Q is the charge passing through some cross-sectional area A and some time delta T. So if you want the instantaneous electric current, that is the electric current at any moment in time, you need to take this expression and take the limit as the time interval goes to 0. Now this leverages calculus. So this is going to be dq dt, and that's the time derivative of the charge with respect to time. So the units for electric current is a well-known unit called amperes, named after the French scientist André Marie Ampere. And 1 ampere is going to be 1 coulomb per second. Notice that amperes are so ubiquitous for electric current that often electric current is called amps. And that's a misnomer because voltage is in volts, but amperes is not in amps. Electric current is in amperes. Electric current is the actual quantity, and amperes is the unit. So don't get confused with the bad nomenclature that exists out there very commonly. The direction of conventional current, I already said this, is defined as the direction in which positive charges flow. The calculations work out the same since electron flow is in the opposite direction. Okay, let us move on. Let's talk about how electric current is related to charge drift speed. Current from charges moves at the so-called drift speed. Let's call that Vd, lowercase d for drift. Imagine that these are conducting electrons. Those are electrons that are actually in motion. If you saw my earlier intuition video, those are the charges that are sort of bouncing around like in an ideal gas, but the ones that are moving in a sort of preferential direction due to the electric field setup. Imagine the cross-section area A, and charges move a distance delta x, and if they move at a constant velocity, that should be the velocity times time, but the velocity is the drift speed. Well, let's also assume that we can define something called the conduction electron number density, a lot of times just called conduction electron density or just electron density. And I'll put that as like the double struck symbol N. And it's the number of fundamental charges per unit volume. So it's going to be number per volume for the unit. Okay, so notice that the average electric current is going to be given by this equation. It's the conduction electron number density times the magnitude of the fundamental charge carriers. So notice that this is an electron. So the magnitude of an electron charge in SI units is 1.60 times 10 to the minus 19th coulombs. We've said this earlier in the course. Times the drift velocity times the area. Now, by the way, the textbook talks about where this equation comes from, but I hope this makes sense to you. How can you get coulombs per second out of this? Well, this is meters per second, and then this is charge, that's in coulombs, but that's going to give us coulomb meters per second. We have to get rid of the meters. In order to do that, we need multiply by area, that's meters squared, and then divide by meters cubed, and then multiply by some sort of number. So it's number per meter cubed, and then that makes sense. So again, this is how all the units work out. I think I already said that out loud. Okay, so let's see if I can move on to the next item here. And let me see if I can move the video up here. Good. Okay. So the current density is another common quantity you should be aware of, and that is the current per unit cross-section area of a wire. So that would be amperes divided by meters squared. Now, current density is often given the symbol capital J. So it's going to be I divided by A, and it's going to be this exact same equation except there's no A in it. So this is just going to be sort of how dense is electric current per cross-sectional area. Now, experiments have shown that charge carriers in metals are negative electrons. It is the conduction electrons that move in a metal, not all the electrons. However, ionic solutions could have positive and negative charge carriers. Okay, now this example I will save for a separate video where I'll show how to calculate the drift speed, but I'll use properties of the conductor element itself, copper, and then I'll show how we can get to this number, okay, using some chemical properties. Okay, so one thing I want to say about electric current is the following regarding the drift speed. Electrical signals, that is charge carriers, set up and move near the speed of light, so on the order of 10 to the 8th or so meters per second. But the charges themselves move very slowly. In other words, they drift at about 10 to the minus 4 meters per second. So that's just a few centimeters per second. In fact, usually only a few millimeters per second. As charges move through a conductor, they constantly collide with other atoms or charges. The average speed of a charge carrier is much like that of an ideal gas, and the average speed is much larger than the drift speed. Okay, so think about this. What this means is when you set up an electric field, the charges start communicating with each other. As soon as one hits, there's another one nearby, hits the next one, hits the next one, do, 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 all the way down, just like dominoes, they start communicating with each other. So that what that means is as soon as you flip a switch in a room, the light comes on almost immediately, basically at the speed of light. So that's just the electrical signal. The charge carriers are sort of like communicating with each other. However, the charges themselves in the direction of interest only move a few millimeters or centimeters per second. So in other words, they move very slow, and that's because the charges really are bouncing around like they would in an ideal gas, but because of the electric field, they eventually make their way in the direction of interest. It's just very, very slow. Notice if an electron also is moving to the right in this diagram with a certain drift speed, the electric field's actually in the opposite direction, and the direction of the electric current, the conventional current, is in the opposite direction. Because remember, positive charge carriers would move left if electrons move to the right. So, if electric charges move so slowly, then how does the signal move near the speed of light? So, when one charge moves into this volume, it increases the electric field felt by the other charges. The change is almost instantaneous. So the increased electric field causes another electron to almost immediately leave that volume. And so what we say is, thus, the signal travels as fast as the electric field near the speed of light, yet the charges have a very small drift velocity. Okay, let's start to talk about how electric current relates to this notion of resistance and resistors. Okay, so if a battery is connected to a simple circuit, so imagine we have a car battery and a really simple circuit. Here's a headlight consisting of a light, and a light we're going to call a resistor. So resistor resists charge flow, but also takes energy away in a circuit. We'll say more about that. And we have wires that current will flow safely. Now this circuit can be represented by a schematic using our device symbols. So these are symbols that I introduced back in chapter 8. Here is a battery with a positive and a negative terminal, long line and short line. Then the resistor, which in this case is a light, is like this heartbeat symbol. And the electric current, in this case, looks like it's going clockwise. Clockwise, that's the direction of the conventional current, that positive charges would flow by convention, from positive towards negative. Okay? So from positive towards negative. Okay? By the way, sometimes batteries are shown to be in red. That's not always necessarily true. And then current can be shown here to be in blue, but that's not always true. Okay, I want to make hopefully what I believe to be a useful analogy for electric circuits and water flow. So the idea is that compare moving water through a circuit to electric current. Notice that if you were pumping water, you would have a pump. But the analogy for an electric circuit is the voltage source. A pump provides water pressure, whereas a voltage source provides sort of a push and potential energy to kind of push charges up. Suppose you have a valve. A valve allows us to stop the flow of water or allow the flow of water. In a very similar way, a switch allows us to allow the flow of charge or disrupt the flow of charge in an electric circuit. And then finally, for this slide, this sort of line takes energy away, if you will, from the water. In other words, it does something and transmits the energy into a different form. And that is analogous to an electric resistor. And an electric resistor takes energy away from the circuit and then transmits it into a different form. So hopefully this is a useful analogy for you to think about. And let's think a little higher, or a little more in detail about this. Notice that if a water pump was maintaining a height difference here, that's very similar to a battery maintaining a voltage difference across the circuit. So a pressure difference can be thought of as an electric potential difference, okay, which the units would be volts. Think of pipes where water flows as electrical wires, and the velocity of water can be thought of as electric current. The only difference with electric current is that it has a drift speed, sure, but current is really the rate at which charge is delivered per unit time. That's why it's in units of coulombs per second. Coulombs per second, which is amperes. And remember, the line we know to be the resistor, and that's resistance. Now, by the way, resistance has units of ohms. Okay? So ohms is, and that's the Greek symbol capital omega. So make sure you have that unit written down somewhere in your notes. Okay, I hope this analogy is helpful. I'll sort of use this analogy at times to discuss electricity flow variables. Let's talk about electric current relationships. So electric current relationships. Okay. So what drives electric current? I. That is charge flow. Well, first thing is voltage. If there's a voltage difference or a potential difference between 2 points, it will cause charges to move. Now, voltage has units of volts. Remember, that's redundant. What reduces current flow? Well, that's going to be resistance. Now, by the way, almost every textbook uses capital R for resistance, but in my opinion, I think that can be confused with radius. Now, a lot of times we don't necessarily deal with circles when we deal with circuits, but it's possible. So I'm going to put it as a script R, but it still looks like a capital R. But the resistance is the property that impedes current. Collisions between charges and atoms in a substance limit current and release energy. The units for resistance are ohms. I already mentioned that. 1 ohm is 1 volt divided by 1 ampere. And then finally, resistance transforms electrical energy into another form of energy, say like a light bulb, a toaster, etc. So let's have a look here. Notice that if we have a light bulb, notice there's a very, very, very thin filament here, which is wound in a very tight helix. And notice that we also have very thin pieces of conducting wire inside this toaster, and that's because it's transferring electrical energy into heat energy. By the way, heat energy usually takes a lot more energy than light energy. Usually a toaster is going to be maybe 1,000 or 1,500 watts. So that might be like 10 or 15 light bulbs. So you typically use a lot of energy when you use heat from electricity. So let's define what we call Ohm's law. Now, by the way, Ohm's law is a central equation to this chapter and the remainder of the semester. And by the way, it's almost as important as Newton's second law in Physics 1. So pay attention to this. Now, by the way, Ohm's law should be sometimes called Ohm's rule because it's only for ohmic devices. Not every device is ohmic, but it's an empirical finding. It's a linear relationship. It exists for most devices. And for the sake of this class, we'll assume pretty much all devices are ohmic. So we'll say that with respect to this Ohm's law, that for a circuit consisting of a single voltage source, like a battery, and a single resistor, like a light bulb, that I equals V over R. So the current flowing in this simple circuit is given by this relationship, Ohm's law. Current is equal to voltage divided by resistance. This is sometimes written as voltage difference is current times resistance. So I equals delta V over R, or delta V equals I times R. Make sure you know those equations. Those are very important equations. So we say the following, that as long as current decreases, that's because the resistance increases for a constant voltage. Now that should make sense to you. If you have greater resistance to charge flow, then you should have a smaller current, and that's because you have the same voltage. But current and voltage are directly proportional. That's because if you have a greater pump for charge, the charges should move faster, that is, with a greater current, for the same resistance, for the same impedance to the charge flow. So I hope that makes sense. Now, let's talk about how to actually measure current and voltage. So what I have here is an electric circuit with a battery and some current, and I have what's called a voltmeter. And a voltmeter is stretched across this resistor. If you've seen my intuition videos, we use 2 prongs, a red and a black prong, in those simulation videos. So the voltmeter would read the voltage, delta V, which is I times R, across this resistor. And delta V is sometimes called the voltage drop. Drop because it takes energy away from the moving charges and takes potential energy away. Now, the only reason the charges keep moving through here is because they have inertia, but they flow through the device, but then they lose their potential energy. Okay? So, in a circuit, okay, the total voltage drop must be that of the voltage source, or else energy will accumulate each time that the charges go around. That's bad. It's bad because if you went around multiple times, you'd build up energy. You could cause a device to explode. Now, by the way, if you want to measure the current in a portion of wire, we would use a device called an ammeter. Notice an ammeter measures amperes, measures electric current. So notice that an ammeter is not across a device like a voltmeter is. An ammeter is in the line of an electric circuit. In other words, the current flows through that device. Okay? So what we say is we often put voltmeters like in parallel to a device, and very little current spritzes through this voltmeter. So voltmeters are generally very safe, whereas ammeters we put in series with the other devices. In other words, we put them in the line of the device. Now, by the way, these multimeters, which are present in the college laboratory experiments, those, and by the way, you can pick these up at hardware stores, you can buy these online. The cost has come down a bit, but they're still over $100 US dollars if you're trying to buy a good one that can do several functions. So you can measure voltage, that make it a voltmeter. You can measure current, that is making an ammeter. You can switch this dial to other settings. You can measure not just DC voltage or DC current. You can also measure alternating current, or you can measure AC voltage. You can also measure resistance with these multimeters. You can also measure what's called continuity. It'll give you a little beep if the circuit is not connected continually. Okay, so anyway, there's a beep in one situation. There's not a beep in the other situation, whether it's continuous or not. Okay, so again, these multimeter devices are very useful for basic electronics troubleshooting. Okay, but you just switch the mode there to switch between voltmeter and ammeter. By the way, it is possible to fry an ammeter because, again, the current goes through the device itself. I'd recommend that most of these multimeters, be they expensive, are only rated for 5 to 15 or maybe 20 amperes. So do a back of the envelope calculation and then make sure you put the setting on 5 amperes, sort of like the maximum current available for the multimeter before you even have any charge go through this device. And then back it off to more fine measurements if you're not getting a very large reading on here. Because always better to be safe than to overload the ammeter version of this too soon. Okay. So let's say more about voltmeters and ammeters. So an ammeter measures current by being connected in series with components in question. So here's an ammeter. Whereas a voltmeter, like I'm drawing here, these voltmeters are parallel across components and they measure voltage drops. Okay. Now, by the way, voltmeters can be put across resistors. They can be put across batteries or real batteries, which are ones that have resistance. We'll talk about that in a later lecture. Okay. Now, I want to briefly talk about reality versus the ideal situation that we'll look at in this class in terms of batteries and wires and resistors. The voltage drop across wires is much less than across resistors because wires have very little resistance. Notice that the voltage, say across this piece of wire, is very, very small in terms of its voltage drop, whereas the voltage drop across a resistor is quite large. And again, across this piece of wire, it's very small, but it's not zero in reality. So for the sake of this class, we'll assume the so-called ideal wire model, that the resistance of the wire is 0 ohms, so the voltage doesn't change across the wire, but then all the resistance is in the resistors themselves. Okay? So that means the change in voltage across a resistor is equal to the change in the voltage across a battery if it's, let's say, a single resistor. Now, let's also talk about something else. Think back to that filament inside of a light bulb. So that filament inside of a light bulb is very thin, and it has resistance, and it has so much resistance that it heats up so that it glows. That's the way incandescent light bulbs work. Now, when I say incandescent light bulbs, I mean older light bulbs that dominated light bulb manufacturing and use probably at least from the 1940s through the early 2000s. And then when there was a switch, starting to switch more so to complex fluorescent bulbs, and then also LEDs, so light emitting diodes. Now, CFLs and LEDs are a little bit beyond the scope of this class as far as how they work. Feel free to contact me directly if you want to talk about that, but an incandescent bulb is basically just a very thin resistor, and that's what we're going to look at here, the properties of the resistor. Let's say if a resistor is thin, how can you determine if it's cylindrical, how much resistance there is? Okay, so let's look at that. What determines the resistance of an object? Well, think about the cross-sectional area, think about the length, and think about the material. So notice that the length of an object is going to matter, for sure, okay? The longer the object, the more opportunities for collisions with atoms. The cross-sectional area of the object, the larger the cross-sectional area, the more easily current can flow. If it's a narrower cross-sectional area, that's like having a thinner pipe, and there's more resistance to flow. And how about the type of material? Conductors allow current to flow more easily than insulators, but then depending on the conductor, there's a different amount of conduction or resistance. So thus, the resistance of a cylinder, area A, length L, is given by the following equation. And let me move this out of the way. So, capital R equals rho subscript R, L divided by A. So the resistance is equal to the resistivity, which depends upon the material, times the length of the cylinder divided by the cross-sectional area. The resistivity is going to be in ohms times meters. The conductivity is going to be the reciprocal of the resistivity. And by the way, the conductivity is sigma sub c. Now, by the way, don't get this confused with surface charge density, which we called sigma before. But the idea is that the conductivity is just the reciprocal of the resistivity. So if something is a strong resistor, it's a if it's a strong resistor, then it's a very weak conductor. But if it's a very strong conductor, it's a very weak resistor. By the way, conductivity would be 1 over ohms times meters. Okay. And by the way, resistivity and conductivity, you generally look these up in tables. Engineering tables, material science tables, and so on. So here's an example table of resistivity and conductivity. I think this is in homework assignment that I assigned, okay? And I'll just briefly say that I'll work out this example problem in a later video. But I just want you to also be aware that this is an equation I haven't presented yet. Interestingly enough, the current density, that is J, which is, remember, I divided by A, is equal to the conductivity times the electric field. Now, I'm not going to show the proof of that equation because that's a little much to do, but it turns out that that's a relationship that you should all just be aware of. But anyway, let's move on. Here's a nice application shown here of conductivity and resistivity. Here's a woman who is holding an electronic device which is measuring her body fat percentage. The device is sending a small amount of electric current through her body. Because muscle and fat have different resistivities, the amount of current that goes from one side of this device to the other as she holds it gives the amount of fat to muscle ratio in the body. Okay, so instead of doing skin fold test, this is definitely going to be a lot more accurate. Okay, so this is a nice example of an application. Now let's talk about how resistance relates to temperature. Temperature is not something we talked about a lot in this class, but hopefully most of you know what temperature is. It's sort of related to the average kinetic energy of the molecules. So resistance increases with temperature because of increased atomic motion. Resistivity is linearly dependent upon temperature. So usually resistivities on those tables I showed you before are for particular temperatures, or we just assume they're constant in this class. But resistivity does depend upon temperature in reality, and it turns out at low temperatures the dependence is nonlinear. Okay, so let's have a look at this. Okay, so notice that resistivity, as temperature increases, we should get more resistance. That's because the more the molecules move around, the more that conduction electrons have collisions with them along the way. Now, if we zoom into this part of the graph, notice that it's nonlinear when you're at very low temperatures. For most substances, the resistivity doesn't go below 0. It approaches some rho sub r, comma 0. Well, here's what's interesting about some substances, though. They have near, not exactly, but very nearly 0 resistance at very low temperatures. So at very low, say, critical temperatures, T critical. And if the resistance is approximately 0 ohms, we give this a very special name, and that's called superconductivity. Superconductivity means when the resistance is very nearly 0, there's a large amount of electrical current possible because the resistance is quite small. Some materials have been found that are superconductive over temperatures of 100 Kelvin. Now, by the way, 100 Kelvin would be negative 173 degrees Celsius. That's still quite cold. But this is a useful and important problem people are looking at. If one of you watching this video is able to discover a substance that operates at temperatures around, say, 300 degrees Celsius, that's sort of an average summertime temperature worldwide, let's say. If you found a material that still had electrical resistance near 0 for that sort of a temperature, you'd probably win a Nobel Prize. You'd probably solve many of the world's engineering problems in terms of electrical transmission. Okay, so anyway, there goes. Okay, how about superconducting residual resistivity? The residual resistivity near absolute 0 is caused primarily by the collisions of electrons with impurities and imperfections in the metal. Remember, a material is ohmic if the resistance is linear in terms of how voltage and current are related to each other. High temperature resistivity is predominantly characterized by collisions between electrons and the atoms in metals. Okay, so the idea is that, like, we might call it high temperature resistance for like devices in our homes, but that's just high temperature resistance compared to other devices you would look at, say, in a lab. And by the way, the value of this critical temperature depends upon very complicated things that are beyond the scope of this class: chemical composition, pressure, crystalline structure, etc. Notice that as the years go on, from 1967 to 2008 in this table, generally critical temperatures are getting higher, although in 2008, that looks like there's a lower temperature there. But notice that we've got these really long and complicated superconductor chemical compounds. And notice that basically these compounds allow us for higher and higher temperatures to get near zero resistance, and so very large currents. Now, by the way, with respect to electricity, there's a lot of bad nomenclature out there. So in a couple of these Chapter 9 and Chapter 10 lectures, I feel like I need to go on some rants. But in order for me to rant, I'm going to give you an introduction and an ending hashtag of rant. So, hashtag begin rant. Electric current in circuits, pitfall preventions, misnomers, etc. It is charge that flows, which is called current. The term current flow is redundant. I've tried to avoid that term as part of today's lecture and in other videos. Sometimes I slip into it, but current flow is just redundant. It's like saying frozen ice. Ice by definition is frozen. A wire is not exactly like a pipe. A wire already has electrons in it, whereas a pipe that you would buy from a hardware store does not. We pay the power company for voltage, in other words, for the potential difference. The electrons are already in our wires. And remember, energy is power times time, like kilowatt hours. So it'd be power times time. Resistance is a property of an object, whereas resistivity is a property of a substance. Okay, so keep in mind, make sure that distinction is clear. And it is not the voltage that kills you with a shock, but it's the electric current. High voltage with big resistance is just a small current. So you see these signs out there, high voltage, is because it's high potential that you could get shocked. But if you have a lot of resistance, you can actually be safe. And one thing I want to briefly also say is be careful with the overuse of symbols. This is resistance, not radius. This is resistivity, not density. This is conductivity with a subscript C, not surface charge density. And this is not wavelength. We do use that symbol as well. And so just be careful with these symbols, okay? And hashtag rant. Okay, so I think that's all I want to say for this lecture. Thank you very much for watching this video. Please smash that like button and give it a thumbs up if you enjoyed this content. Please subscribe to the channel and share this video with others in your sphere of influence. And I will see you in the next video. Thank you for your attention.